Hello. Well, here is my interactive PLS path modeling application. This application was developed using the Shiny package in R. The Shiny package permits one to use R functionality, but to develop a web-based application. And you can see it runs in a web browser. You don't have to know anything at all about R to use this application. That's the whole idea. This is a more user-friendly front end than R is for non-R users to be able to access the functionality in R. And in this case, it's the PLS path modeling functionality, which is really quite extensive. So how does this work? Let me just show you some of the features. Right now, there are only two ways to input data and models. We don't have a GUI interface, but we will before too long. One way to do it is to load in a Smart PLS modeling file. Another way to do it is to load in two very short worksheets, one that indicates the structure of your measurement model and one that indicates the structure of your structural model. Let me show you how to do it. First of all, you got to load in data. Everybody needs data. Okay, so let me demo a couple of packages, a couple of models here. This is a variant of the TAM model. So we load in the data for the model that's a CSV file, and you see it right there, TAM 1190. And the first thing that you can see in the application, it will show you all of your data. In fact, every single line of it. This file has 1190 records, so you have visibility on that. And then you need, in this case, we're going to load in a Smart PLS SPLSM file, SPLSM modeling file. If you're not familiar with Smart PLS, here I can show it to you. So here's the first model that we're going to look at. As represented in Smart PLS. Smart PLS is a wonderful PLS path modeling tool. It was developed by Dr. Christian Ringel, who's a full professor in Germany at the University of Hamburg, and it's a path model. And so if you draw your model here in Smart PLS and then you simply save your model, you say File Save, then you can load it directly into this interactive PLS path modeling application that I'm showing you here. So let's do that. We'll load in the SPLSM, the modeling file from that TAM model that we just looked at. So I load that up. And Shiny has some unique features. It's reactive programming. That is, you can suppress this feature, but it's reactive so that whenever you change a parameter or you load a new file, it will immediately react, so to speak, and compute, do whatever it's supposed to do. Now, there sometimes is a lag. For example, if there's an extensive computation, as PLS path modeling can be, it might take a few seconds, perhaps 20 or 30 seconds for everything to show up. But so here it took the data and it took the model, and here are our output reports. This is the overview table. Here is the cross-correlation matrix between the latent variables. Here's the report for loadings and cross-loadings. Here are direct, indirect total effects for this model that was just loaded. Here's outer weights and loadings. Now you can run group differences. I'm not going to do it on this. You can also bootstrap. You'll note right now all of the bootstrapping reports are empty. So let's do that. So we'll come down here and we'll say run bootstrap validation. It's turned off by default, so you can turn it on. So we'll check that on. And you have a choice. Notice this is a slider, and we've limited the bootstrap resamples to 500. The various reasons why. Note every time I change this value, it's recomputing. So let's just do it 200. We'll do 200 bootstrap resamples, and this will take just a minute. So I'll pause the recording. And so when the bootstrap resampling process completes, these reports are populated. And so we have, for the bootstrap, we have 95% confidence intervals for these. This is path coefficients. These are the direct effects. Then we have as well as for R squared. What's perhaps more useful about R is you get a lot of interesting, good plotting capabilities in R. So this is just a basic plot of the inner model. Here's a plot separately for each of the blocks, the outer model. These are the loadings, and then where these are the latent variables: perceived ease of use, perceived usefulness, attitude, and these are the indicators or manifest variables, and here are the loadings for these reflective items. Many people don't know this, but every measurement block, whether it's formative or reflective, any PLS path modeling algorithm will estimate both loadings and weights. These are the loadings. Here are the weights. We have group differences. We're not going to look at that now. There's a hierarchical cluster analysis. I'll skip that right now. Here's the evolution of the outer weights as the algorithm executes. This is a very interesting plot, and I'm not going to get into it in a great deal of detail, but this model converged in 6 iterations, but you can see how the weights change from each iteration, which can be useful to understand the effects of the data of the individual blocks and some other characteristics about. Here are the LV scores, latent variable scores. These are the computed scores. Of course, latent variables don't really have scores. That's one of the unique characteristics about PLS path modeling. It estimates them for you. Note this data is very left skewed. And that's not a problem in PLS. In fact, that's one of the strengths of PLS, that you do not have to have normally distributed data, as you can see here. These are the estimated calculated values for the latent variables. We have the predicted values. And then, of course, just like in any other estimation, if you have actual values, predicted values, you have residuals. So that's kind of a neat feature. This particular application will be one of several that I am assembling that will fit together components and be related. Here's a little page that talks about why it was developed and who we are. Right now it's an application of this organization, SEM'n'R.